Okay, great. So let's welcome Rajesh Narayanan from IIT Madras for the talk, for the last talk of the morning session, who will teach us how to kill a Griffiths phase. So Raj, over to you.
So before I start, I would like to thank Yasir and Ronny, who's not here, for inviting me to this wonderful conference. I'm usually a very non-violent person, but I actually will tell you how a Griffiths phase can be killed. And I think in an audience of experts, I don't have to tell you what a Griffiths phase is, but I will definitely tell you what it is and how to kill it. So this is actually a joint collaboration between experimentalists led by Avik Bede and his student, who is very good, Simrandeep Kaur, who did all the measurements, with Thomas Boita and a bunch of other people. And this has just got published in New Journal of Physics. So what is it that I'm interested in this talk? So what I'm interested in is to look at superconductor normal state transitions. And the superconductor normal state transition is a quantum phase transition that is actually controlled by effectively using the magnetic field as a tuning parameter. And specifically, what I'm interested in is the role that disorder or impurities plays at this transition. I'm a very simple sort of guy, so this is going to be very much an S-wave sort of thing. So the typical way how one would deal with such transitions is that you start out with an effective microscopic description. You look at the Cooper channel density. You decouple the Cooper channel interaction by means of Hubbard-Stratonovich field. In this case, I have written it in terms of this object phi. And what you do is you integrate out the underlying fermions and derive an effective order parameter theory or LGW theory. The integrating out of the underlying fermions is problematic for certain cases. For example, in terms of ferromagnet, for the itinerant ferromagnet, this can lead to very interesting complications. But in the case of the superconducting order parameter or the antiferromagnetic itinerant antiferromagnetic system, it doesn't give you any such complications, or one supposes it doesn't give you such complications, and you get an effective field theory. The effective field theory is the usual phi-4 theory, with the only wrinkle in this case is that you're actually dealing with a quantum phase transition, so the imaginary time comes into picture, and this is given by this d tau. This delta naught actually encodes the distance from criticality, so this is essentially b minus bc for you, right? And this mod omega, which is actually very important, effectively is the damping that is given by the underlying electrons or the electronic fluid. And this is what is called as this Landau damping. So effectively, the Gaussian fixed point is given by z equal to 2 dynamics, and that is actually going to be also important for us. So this mod omega sort of damping is, if you do a Fourier transformation, essentially become a 1 over tau minus tau prime square interaction in imaginary time. Right? So this is an old way of doing things, in the sense that it's a very well-established way of doing things. You can see it in the original paper of Hertz, Millis, and for the itinerant antiferromagnet, this was essentially Bellis and Kirkpatrick, who essentially looked at it, or initially looked at what would happen if you add disorder to the system. So this is actually the plot of such a transition that one sees as a function of the distance to criticality. And what we are going to show is we are going to explain we are going to explain disorder effects around this critical point at BC. Yeah. Yes. It is a superconducting order parameter. So you couple it to the NC bar. So it's effectively integral ddx d tau del square plus delta NC plus delta star NC bar. That one, or delta NC bar delta NC. That's what. So this is that delta. So the initial attempt at doing this essentially implied that you take your distance to criticality and you make this as a random function of position if you have impurities in the problem. So for most field theorists, the natural tendency would be to take this model and to replicate it. Integrate out the disorder by using replicas because it's an interacting field theory, and then you integrate out the disorder, and then you do renormalization group. And this was done by Belitz and Kirkpatrick a long time ago. And what they found was that you get a random fixed point that only exists in a window of disorder strings. Okay. Later on, myself with Belitz and Kirkpatrick and Thomas essentially looked at what would happen if you add rare region effects, which we'll look at in more detail. But what happens is that there is always going to be runaway flow once you add these rare region effects, or which I'll talk to you in more detail about in a second. An alternative approach was actually was taken forward by Thomas Vojta and Jose Hoyos quite some time ago, and their idea was to use what is called as the strong disorder renormalization group sort of approach. So what they did is that instead of working with a theory where you integrate out the disorder and work with an effective field theory with an effective disorder strength and do a perturbative RG calculation, what they did is to adapt approach called the Dasgupta-Ma renormalization group, which is also put in more firmer footing by Daniel Fisher. They tried to use such a theory to understand the disorder effects in this problem. So what do? What they do is they discretize the 5-4 theory, go into the large n limit, and then effectively get a theory where you have two sort of competing parameters. One is a local gap, which is given by this epsilon I, which comes out of the distance to criticality plus some sort of self-consistent term, and this J that favors an ordered phase. So when epsilon is large, you essentially live in the disordered phase or the normal phase, and when J is large, you essentially order the superconductor. So what you do is you essentially have a competition within epsilon and J, and this epsilon and J competition, they essentially put on a firmer footing, which is called the strong disorder renormalization group. So what is this strong disorder renormalization group? It's a real space sort of treatment, where what you do is at every step of the renormalization group, you go in and you figure out what's the strongest scale in the problem. If the strongest scale in the problem is the gap at any certain site, which is this epsilon I, not the superconducting gap, but this distance to criticality, if at some site epsilon is the largest, or that's the largest energy scale, then what you do is you integrate out the largest energy scale by means of a perturbative treatment. Okay, so if you integrate out, for example, if epsilon 3 is the largest energy scale, you integrate it out, and then what happens is this short range term that does not actually have a coupling between the sites 2 and 4 now gets coupled by a weak coupling. So at every step of the renormalization group, what you do is you either integrate out a site or you integrate out a bond. In this case, you're doing a site decimation. If you do a site decimation, the two sites 2 and 4, which are not coupled in the beginning, then gets coupled via this effective renormalized coupling J, which is actually weak, because the strongest bond epsilon, or the strongest energy scale epsilon 3, comes in the denominator. Yeah. Yes, this is in 1 plus 1. Yeah. Yes, but that is coming from the higher. Yeah, that is coming from the higher dimension. And then what I do is I take that model and then I discretize it, and I can do this, at least the semi-discretization, quite naturally. And this works in the large n limit. That's a problem here. In a similar vein, what I can do is, if one of the strongest coupling scale is J2 or some bond string J2, I can fuse these two rotors together. And when I fuse these two rotors together, they have an effective distance to criticality, which I call epsilon twiddle. And this can actually be calculated once again in a perturbation series, in a perturbation theory. And what you see is, once again, this J2, or the strong scale, comes in the denominator. What you should see is that there is a duality that exists between the renormalization recursion relation of J twiddle and that of epsilon twiddle, both have exactly similar structures. So this was actually something that was discovered first by Daniel Fisher in his analysis of the transverse field or the random transverse field Ising model. The recursion relations are almost exactly the same. If the recursion relations are exactly the same, one can effectively borrow the results in toto. So in effect, what it says is that the critical behavior of this model in 1+1 dimension is essentially that of the infinite randomness universality class. What do I mean by that? What I mean is that, for example, if I look at the correlation time at a conventional transition, we all know, and we teach that in our not our freshman courses, but slightly advanced courses, that the correlation time essentially scales as the correlation length to the power of a dynamical exponent. Correct? Now, if you go through this usual universality class, but this special universality class of the random transverse field Ising model, and now of the superconductor insulator transition, the fixed point actually admits a new universality class where the log of the correlation time goes as the correlation length to some power. Okay, so it's a new universality class. Actually, there are much more important things that come out of here, namely that if I look at the distribution, so if I look at the distributions of the coupling strengths, this essentially becomes broader and broader as you approach the infinite randomness critical point, which means the rat regions becomes more and more important. So this was also extended to the case of super-ohmic damping, so where this omega, instead of just having a mod omega, you have omega to some other power. We have actually looked at it, and we find that this essentially behaves like some disordered KT. So what does that mean? That means that for the infinite randomness, for the superconductor insulator transition in the presence of disorder, the system goes through a new sort of critical point, and this new critical point is of the infinite randomness universality class. So the question that one can ask is, how do you actually see these effects, right, in a real experiment? So one of the smoking gun signatures of this thing is that if you're away from the critical point, if you say you're coming in from the ordered phase and you're approaching the critical point, then if you measure the correlation time, then this correlation time essentially diverges as a power law as usual, but you're not at the critical point, but coming into the critical point. Then it diverges as a power law, but the important thing is that this exponent that controls the divergence essentially also changes as a function of the distance to a critical point. Okay, it's not a constant. It changes as you approach the critical point, it changes as a function of the distance to a critical point. This delta naught is essentially related to your B minus BC. So the smoking gun signature of any of these Griffiths effects, or any of these infinite randomness associated effects, is the presence of a non-universal exponent as you approach the critical point. So that is what we are going to be looking for. So there is a very interesting way of how one could actually think about this infinite randomness physics and the fact that you have a correlation length that diverges near as you approach the critical point, and this divergence is controlled by a non-universal exponent. Essentially, one can think of this in terms of rare regions. So what are these rare regions? These are regions of local order when the bulk is still in the disordered phase. The way one could think about this is that if you have such regions of local order, then at zero temperature, these regions of local order are infinitely correlated in imaginary time. So that means the dynamics of these rare regions are extremely slow. It takes a long time for these rare regions to flip. What you can show is that in the sort of situation we are in, these rare regions are exactly at the lower critical dimension of the system. And since they are the lower critical dimension of the system, they have the exponentially large sort of susceptibility. You compare this exponentially large susceptibility with the probability of getting such a rare region, which is exponentially small, and you get these power law singularities. And this power law singularities is what leads to the correlation length diverging as a power law with a non-universal exponent. Okay. So if you want to read more about this, there's a fantastic review by Thomas Voita where he actually looks at this in much more detail. So now let's look at this data that Avik's group actually produce. If you look at it, then essentially you see that there's a critical point at this BC, where essentially the system goes from a superconductor to a normal state. But if you essentially zoom into here, into this crossing point, you actually see the crossing points actually drifts. Okay, this crossing point actually drifts, and this drift in the crossing point can be explained by means of a leading irrelevant operator. So if you have a leading irrelevant operator and you are at this infinite randomness critical point, then you can easily explain this drift in the crossing points. And so that's one very interesting way of actually figuring out whether the critical point is given by this infinite randomness fixed point. So now what is our strategy? So if you want to look at the smoking gun signature, you want to extract this exponent nu z, because if you extract this exponent nu z, then if this exponent nu z changes with b or with the tuning parameter, then essentially it says that there is a possible Griffiths phase around. If it's a constant, then it's just universal critical behavior, right? So this is what a weak student did. What she did is she essentially did from this set of magneto resistance isotherms. What she does is she takes three of these isotherms, essentially looks at their crossing. This crossing gives us the RC and the BC, and then she does a data collapse. This data collapse effectively gives you effective exponent nu z. This nu z exponent, essentially what she does is she plots this nu z exponent as a function of the field. What you see is immediately a very interesting feature where you actually see that the nu z actually diverges as you approach the critical point, exactly as one would predict in the theory, or as exactly as was predicted in the theory. But here is a new, so this sort of divergence is not anything new. It was observed earlier in papers by Llewellyn and Xing, and for T greater than some 7 millikelvin, everything seems hunky-dory. But what is actually the problem is that below 0.07 Kelvin, there is actually a second divergence that creeps up. Okay, so instead of having just one curve that actually diverges as you approach a critical point at somewhere around 0.179, you essentially see two divergences. So there's a kink-like feature which is not present in the other papers that actually report Griffiths-like effect. So this is something which is completely new, and it is not consistent with whatever is known. See, the point is, what we are doing here is, this essentially assumes that there is a power law scaling involved. So whatever interesting features is there is encoded in the effective divergence of nu z. Okay, and we can show that if the effective nu z should have this 1/log dependence in temperature if it has to be consistent with the infinite randomness fixed point predictions. So this second divergence is something which we don't know. So what we do is we plot the 1/nu z as a function of temperature. Okay, so for large enough temperatures, essentially the 1/nu z effectively exactly fits the predictions of the infinite, the predictions of the infinite randomness scenario. So effectively, for large enough temperatures, you follow this dotted line, which is essentially this log dependence. But as you come smaller in temperature, then what happens is this essentially takes off as a power law. Now, this power law divergence is actually incompatible with the very notion of a critical point, let alone an infinite randomness critical point. If this diverges as a power law, then it essentially means that there is no vanishing energy scale as you approach the transition. Okay, so there's lower temperature. At lower temperature, we show that you have some behavior which is not even compatible with a quantum critical point. Okay. Yeah, that's a good question. There is an anomalous metal phase in this. Yes, exactly. Yeah. So but the point is that something destabilizes the quantum critical point. That's my statement. That the quantum critical point is destroyed. Until a certain temperature, you have all the features of an infinite randomness controlled quantum critical point, and below a certain temperature, it is lost. That's exactly what I mean. So I'll come back. I'll come back to this. So maybe one possible way around it is by saying that, well, look, what you're doing is you're actually forcing the system to follow a power law scaling, even though albeit with a 1 over nu z, which is temperature dependent. When you know very well that actually at the critical point, at the infinite randomness critical point, the scaling behavior has to be activated of this form, right? So what we do is we take our data and we try to fit this or collapse it by means of the activated scaling ansatz. If we do that, what we again see is that the high enough temperatures up till like 0.07 Kelvin, everything collapses beautifully onto two curves, right? But below that critical temperature, what happens is the data collapse just breaks down. You cannot get, by any hook or crook, you cannot get it to map onto, or to collapse onto a universal curve. Again, stating that there is something that goes wrong below T less than 0.07 Kelvin, right? So to summarize, what we are saying is that at temperatures below 0.0 Kelvin, 7 Kelvin, there is something that happens that actually destabilizes the infinite randomness fixed point, the infinite randomness fixed point, and we do not know what we get, what sort of correlated material or slush we get below those temperatures. So at this point, we throw up our hands and we decide that let's try to make up some sort of a scenario where such a thing can happen. So one possible scenario is given by this old paper by Dobrosolowicz and Miranda, where they looked at similar sort of systems, but what they do is that they have rare regions in the system, but these rare regions also have in the background an RKKY-like interaction. So each of these bubbles over here is a rare region, and they are coupled to each other via long-range interaction. So the phi's are the phases in our model are the rotor degrees of freedom in the model of Dobrosolowicz and Miranda, where they were looking at some sort of a ferromagnetic system, and they're essentially coupled to each other by this RKKY, or in our case, a long-range interaction. So what do you do if you're faced with an object like this? What you do is you do a replica average. So the replica average effectively gets you a quartic term. Then what you do is you do a Hubbard-Schroeder image transformation and essentially evaluate this object Q alpha beta that couples to this phi correlator in a self-consistent or a saddle point sort of in a saddle point or a saddle point approximation. If you do that, then what happens is the effective interaction between these star regions essentially gets modified. They get modified because what happens is you have to remember that you're in a Griffiths type phase. The Griffiths type phase, the density of states goes as a power law. If you essentially use that fact, you immediately see that the dissipation term essentially gets modified or renormalized. So what it is telling us is that there is one more aspect of dissipation that comes into being, and that essentially comes from this long-range nature of interaction that is actually playing with the rare regions. So if you take that into account, then you essentially find that this mod omega term that comes from the Landau damping essentially gets renormalized now and then becomes a mod omega to the power d by z minus 1. Now this is actually important because if you're in one dimension, and if you're looking at rotors with xy or higher symmetry, or Heisenberg xy or higher symmetry, then if you just go below this power 2, if you just go below power 2, the rotors can order by itself. So what happens over here is that in our case, what happens is there are these rare regions. On these rare regions, there are these fluctuating phases. These fluctuating phases, because of the presence of this long-range interaction, essentially now starts to see an additional dissipative environment. This additional dissipative environment is such that it's good enough for this infinite change to essentially, that comes because you're in the quantum system, to essentially phase lock. So each individual rare regions now starts phase locking. That means they get ordered by itself. That means the system actually starts, the transition actually smears. Okay, the transition actually, so because each individual rare region is ordering by itself. So that means that as each of these rare regions it orders by itself, that there should be a tail that develops, right? Because you will find with exponential small probability some regions still ordering in there. So if you do that, then this is the sort of picture that you have. There's an interplay of long-range interaction disorder, right? There are these individual regions essentially phase lock, and so you can think of them as individual Josephson junctions. So each Josephson junction undergoes a transition by itself, and this essentially provides a tail to the phase diagram. Now what happens is, so now it comes to the question of this strange metal. So each of these are essentially phase lock. You can have hopping between these rare regions by Cooper pairs, and this possibly could be a generation of this anomalous metal, right? So if you essentially plot the phase diagram, indeed what you see is that you can fit until up to some very low temperatures. This phase diagram exactly follows that of the infinite randomness physics. But then it starts developing these tails, and we believe that these tails are actually a result or are related to the smearing of the quantum phase transition. And we believe that this is actually going to happen in all other materials. And that it's just that we have not gone to low enough temperatures to see this. Yeah? Yes. So some long range, but here it can be some Friedel type.
So how does that long range interaction physics play out as a function of
Magnetic?
Is it there?
Yes. Okay. So the question is, what temperature scales do you see this at, right? So yeah, so you can show it depends on the system. It's some microscopic parameters, but you can show it is an exponential small dependence on it. So there is a window, and you can calculate this window, and you can show that it's exponentially small. So it could just be that in this material that microscopics just conspire in such a way that you can see it. Otherwise, you might have to go to very, very low temperatures. No other Griffiths experiment has seen this thing yet. So what we have found in this case is that the Griffiths phase essentially is destroyed at extremely low temperatures. What we don't know is what is the nature of the ground state. I have not said anything about the nature of the ground state. I've just said that there's a possibility that the infinite randomness fixed point is destroyed. But what is the ground state? Is this an anomalous metal? What is it? We don't know. Question is, how generic is this mechanism? And for example, if you take the other papers that have seen this, if you go to low enough temperatures, do we always visit such sort of of a smearing scenario. This is something which we are working on. The actual proof of the pudding is, I mean, we have just smelt the pudding being made, but the actual proof is if we can do a real strong disorder renormalization group by putting in some sort of long range interactions and seeing clearly that, you know, at a temperature, at a temperature that is set by some microscopic parameters, the Griffiths phase is seen, and beyond this, it's essentially lost, right, or it's cut off. This is something which we plan to do at some point, but we have not started doing it. So this is, so the question is, how universal is this sort of behavior? And that's something which is an open question and which we are trying to do. Thank you.
So in the smeared picture, when each junction, each grain orders on its own, is it like a spin glass, XY spin glass?
Yes, there is a possibility that there is a spin glass.
Yeah.
So in the paper by Dobrosolovich, there is what is called as a cluster glass. That
I see.
And so there is a possibility here that there could be an equivalent of such a glass.
Okay, but then you would expect memory dependence and, like,
yes.
you know, free, you know, history and all that stuff.
Yes, but I can't deal with that in this sort of framework, right?
No, I mean as an experimental test, you know, if you.
So you mean
look at
you
some
want to do
AC
some sort of hysteresis stuff?
Yeah, or you know, like, you know, at least in a usual spin glass, you look at zero field cooled versus finite field cooled, that kind of thing.
Right. Yeah, I don't think that Avik and Simran have done this. But what would you look at? Because we are looking here at the conductivity, right? I mean, not. See, there you have access to an order parameter in some sense, right?
Yeah.
Yeah, it's a conductivity, which is not really an order parameter in that sense.
Right.
So
maybe if you tunnel pairs or something, you know, with an ordinary superconductor.
Right.
Look at the pair susceptibility.
Yeah. So what is interesting is to see this sort of stuff. You need the anomalous, or at least all the papers that I have seen of. Whenever you have the Griffiths effects, you also always see an anomalous metal coming out of it. I don't know whether there's a deep connection between these two, right? There could be, I don't know.
Okay, if it doesn't seem to be the case, then let's thank Rajesh again for a very nice talk.